Good afternoon. Welcome to Krishna's classroom. In this talk, we are going to explore the question, why should we go for a completion of a measure space? This is the central theme that we will explore in this talk. And we have already introduced that for every measure space, a completion exists. Let us recall some of the analogous situations. You recall that when you have a metric space, then you talk about its completion. Or when you work on a normed linear space, we talk about its completion. And there we proved that for any given metric space or normed linear space, it has always a completion, which gives which leads to the concept of complete metric spaces and what are called Banach spaces and so on. Yeah. So now the question there was, why do we do this? The reason was, when we do analysis on such spaces, we should be comfortable in the sense that suppose you take a Cauchy sequence of elements in a metric space, then it should converge within the space itself. Now this is what is called facilitated only if the space is complete. In that case, you don't have to bother about the problem of getting away out from the space while chasing the elements of a Cauchy sequence. Otherwise, if the space is not complete, you get into very meaningful convergible sequences which do not have a limit in the space. Now, this will create some problem while doing analysis. Do you have a similar problem here? Why do we, after all, seek a completion of a measure space? So let us recall. We have shown in our last lecture that given a measure space, there always exists a completion. Now, let us fix the notation. Let X, M, mu be a measure space. That means X is the set on which the measure space is built. M is the set of all the sigma algebra of subsets. Mu is the measure that you have. Now, we felt that there is some comfort that we derive when we seek a completion, and we will revisit what exactly is the completion and so on, which leads to a more number of what are called elements in the sigma algebra, and then again defining or extending measure to the concept of measure to consistently with the space that we were working on to this larger class. This is what is called completion. But the question that is not very often very clearly answered or made explicit is, why do we do this? What is the reason for this? Is there any specific reason or advantage that you derive by doing it? Okay. Now, in this context, we started by introducing the sets of measure 0. And a property defined almost everywhere. Now we introduce the concept of sets of measure 0 and properties defined almost everywhere. What are they? And what was the reason for introducing these ideas? Let us ask this question. Now, in this context, we recall Riemann integration. Take RAB, where AB is some compact subset of R. This we designate as Riemann integration. Space of Riemann integrable functions. Now, on space of Riemann integrable functions, if you consider a function f belonging to RAB, then modify it by redefining it to G, by redefining it on a subset which has the property designated as null set. As null set, then integral AB of f is equal to integral AB of G. What does it mean? We allow or we change the function f on a what was called a subset of AB, which was called the null set, called a null set. I mean, it has the property of a null set, I mean, which we have defined very explicitly while introducing Riemann integration. Please recall. And you can immediately realize, having done Lebesgue integration theory, you can immediately recall that these null sets are the forerunners of the sets of measure 0. 0. So on the null set, for example, the example of a null set is you take all rational points on the interval AB, just form a null set. And suppose you take the function f defined on AB. Now redefine f or redesignate f on at the sets at all rational points and define a new function g. Okay, keeping f as it is on the, or let me be a bit cautious here. Okay, let me take a finite set of points on AB and let us redefine this function at these finite set of points and then call the new function as g. And this g, although is a function different from f, it's not identical with f. Although it agrees with f at all points other than these finitely many points where we have modified it. Okay? When we feel that this happens, integral AB f equal to integral AB g. I mean, that's an example which we are familiar with. What is the reason for that? The total length of the points, of the content of this finite set of points by way of length, okay, is 0. So we go to the next level when we introduce the Riemann or Lebesgue integration. We introduced or we established that there exist subsets of the real line with measure 0. Okay, and you see that every null set on the interval AB is a set of measure 0 because we were generalizing the concept of Riemann integration to Lebesgue integration. That's why I said the concept of null set is a forerunner of the concept of what you call the sets of measure 0. This keep in mind. And then what we have observed is that as far as integration goes, these two functions have the same integral. Now this plays a very, very crucial role in working on the integration theory. Now let us come to the present scenario. Okay. In the present scenario, we will be working with measurable functions. Before we talk about integration. Now let us be very precise about the sets of measure 0. Okay, or what you call the next level of the concept, namely some property is valid almost everywhere. Properties defined almost everywhere. Okay, what is it? For example, in the same scenario you take, we say that if we call this a property P is said to hold almost everywhere where you have the standard notation AE, if P is valid everywhere, except on a set of measures 0. For example, suppose you have a measure space. Suppose you have a measure space X, M, mu. And consider what are called functions defined on Fn. Functions f and g defined on X. They just real value. Suppose f is from X to R, g is from X to. In fact, you can replace this R by a topological space in more general scenario. Let us not do that at the moment. Now, we say that f is equal to g almost everywhere on X if the set of X belonging to X where Fx differs from Gx has its measure equal to. This is the definition. Okay. We say f is equal to g almost everywhere. So the property that we are now considering is the equality of two functions. Okay. Then we say f is equal to g almost everywhere. So that's an example, and that's a relevant example that we'll be interested in at the moment. Now let us proceed further and you recall the measurable functions. Measurable. Say that f from X to Y a topological space is said to be, we have this one, measurable if f inverse of V belongs to M for every V open in Y. This is the definition of measurability. This is an essential feature that is required to talk about integration, as we have seen already. Okay. Now we have now the following scenario. You have X maps from X to Y, and this we accept as the class of measurable functions. Now recall that Suppose you have, see, this is your x. You have a set E, a measurable set E. So E is contained in, or E is an element of, or E is a measurable set. And also assume the measure of E complement equal to 0. Okay. Then we can talk about a larger class of measurable functions. What do I mean by that? What I seek is this. See, suppose we say that we modify this definition. Okay, we modify this definition by requiring that, see, this is your P contained in Y open. This is F inverse of V, and you take the intersection of F inverse of V with E. Remember, E complement has a property that its measure is 0, and we redesignate measurability. We say that F is measurable if there exists a set, measurable set, E belonging to M, such that measure of E complement is 0 and F inverse of V, F inverse of V intersection E belongs to instead of saying F inverse of E, V is measurable for every V open or V belonging to tau. Tau is, you have Y tau. Okay, so we have Y tau is the topological space that we're talking about. So we have modified it. Okay. Now with this new definition, what you demand is that you are not asking for F inverse of the whole of F inverse of V to be a measurable subset of X, but you require for this E, F inverse of V intersection E is measurable. And outside, because see, what we are slowly gravitating towards is that it is immaterial how you have your F outside. Okay, so you clearly see that all measurable functions in the sense of this definition that we have made earlier satisfy this property. Now, all measurable functions in the original sense are measurable in the new sense. Okay. This is the important part. However, there exists measurable functions in the new sense failing to be measurable. Failing to be measurable in the original sense. So we have two concepts now. Measurability in the original sense and measurability in the new sense. The measurability in the new sense is what we have said here. F inverse of V intersection E belongs to M, where E is a measurable subset of X, and having the property that measure of E complement is equal to 0. Okay, let us see how such a scenario can arise. Now you see, you have E, and this is your X, and this portion is what you call E complement. E complement and measure of E complement equal to 0. Okay. Now we have seen that there are when you define a measurable space, even Lebesgue machine, okay, there are subsets of R which are not measurable. Okay, so you cannot make a very general statement that if a set is measurable, all its subsets are measurable. That is not possible. Okay, therefore, you see that there may be, so there may exist F contained in X, E containing F, such that F is not measurable. That is, F does not belong to F. F does not. This is quite possible. We will take such a set. Okay. Remove this now and I'll reprint all this. Well, I require it. Okay. So we take such a set. Non-measurable the measurable set with measure of E complement equal to 0. So we have this is the scenario X. This is where we are working. Okay. Now let us consider a function. In the new sense, that means you have got F inverse of V intersection E belongs to M. For every V open okay, as I said, you cannot say that F is measurable. Okay, for instance, what I am going to say is that you cannot say that F is measurable. One cannot say that. Original sense. Okay, we are going to work on this. Now, what we do is the following. We construct a function. We construct a function G to R, which is not measurable in the original sense, but measurable in the class case. In the new sense. How do we do that? Okay. Now, let me assume we start with a function f that is measurable in the usual sense. Measurable not. That is, we are taking f inverse of v that is belonging to norm. We start with such a function. Now from that we are going to construct a function which is not measurable in the original sense but measurable in the new sense. Okay, how do we do that? Okay, so define f g from x to r by setting gx equal to f of x. That means on E, f and g coincide. F is not measurable. That is on G. Coincide. Now on f minus e, equal to c, a constant. Now remember, f slash e is not measured. Because f is not measurable, but e is measurable. So f slash e is not measurable because f is the union of e and f slash. Had this been measurable, f also would have been measurable. Since f is not measurable and e is measurable, f slash e is not measurable. Okay, now let us define, on f complement. On f complement, you set the function. G equal to 0. Now you see that f complement is not measurable. Then you see that you immediately see that then G inverse of V, G inverse of V may not be measurable. May not be measurable. For instance, suppose you take any V, okay? Suppose you take any V which does not contain zero R, but has C belonging to, we are taking C not equal. C not equal. Then what happens? Then one can clearly see that G inverse of V contains the entire F minus E. Okay, the portion of E where the function is not equal to 0. Okay, then G inverse of V is equal to what? The entire portion of E where G inverse of E is, because you have started with an F which is measurable and so on. So you see that this function would fail to be a measurable function because this portion is not a measurable part, and that is fully completely inside that, and the other part which is there is a measurable part. So it is the union of in fact the disjoint union of a measurable set and a non-measurable set. Hence, not measurable. Which implies G is not measurable in the classical sense, in the original sense. That's a problem. But is G measurable in the new sense? We will investigate. You immediately see that whatever be the situation, you see, G inverse of V intersection E is G inverse of V intersection E is measurable. G inverse of V itself may not be measurable, but G inverse of V intersection E is measurable. Okay, that is because you see that you are only considering the portion of G inverse of V inside E. Therefore, this is contained in G inverse of E is contained in E. And of course, one can argue that after all they differ only by some values. Okay, you can easily check that this is a measurable. I mean this set is a measurable set. Consequently, G is measurable in the due sense but not measurable in the original sense. That is, for a given f, restricted to E, there exists non-measurable extensions to So the meaning is this. You start with a measurable function. Take its restriction to restrict it to E. Okay? No, what I wanted to say is start with a measurable function, take its restriction to E, which is a measurable function. Okay? Now extend this to the whole of x in the following way. Assume there exists a non-measurable function. Okay? Such that it contains the measurable set E. I mean, this is quite possible. Okay? Now, as I have designated here, extend f restricted to G. Sorry, f restricted to E to the whole of V by redesignating it. Now I have shown that this may not be a measurable. So there exists non-measurable extensions. Now this is a problem that we face. Okay? Right? This is because of the existence of a non-measurable subsets for a measurable sets. See, all these problems arise because one cannot assert that all subsets of a measurable set measurable. Now this is a problem. So the crux of the problem lies in this. Now how do we address this? Okay, such that what we want is this: on E, see, we have X, E is there, E complement is there, measure of E complement equal to 0. Now suppose a function is measurable on E, okay, right? Not in the classical sense, but with reference to E. Okay, then what happens? What we are saying that we would like all extensions to X, B, measurable in some sense. Some new sense. Okay, so we address this problem. How do we address this problem? And once again, we go back to see that our objective is this. Suppose G is any extension of that is G restricted to E is equal to F and G is not equal to F. Then G should be what was the difficulty? The difficulty is that we don't have sufficiently many measurable subsets. Okay? So you see that, immediately observe that we do not have sufficiently many measurable sets subsets of X in to serve this purpose. Just make the observation. Suppose we postulate all E complement in the new sense. Then we observe that any extension f from E to x is measurable in the context of the framework of the enlarged sigma algebra. Now, how do we achieve this? Okay, we achieve this as well. Now, this is done. We have gone through that. What are the steps? We had E is contained in that. E belongs to, this is the scenario. Then measure of E complement equal to 0. Now we define the following. So define the following. Let such that A belongs to M and B belongs to M. That is, A and B are measurable sets. Okay. and A and B belongs to with a further property that assume the measure of we use the notation P slash A or it's the same as this. So don't be confused by the notation. Then we set C measurable. And mu of C we define as mu of. So this is what you have. You have on X is your A is measurable, B is measurable. Now the measure of this equal to 0. Now you take a C which is some subset of this. We are not putting any restriction on it. Now we postulate that C is measurable in the nuisance. We set C to be measurable in the nuisance. And mu of C to take as mu of. Okay. That means all subsets of A squeeze, all subsets of B squeezed between A and B are now going to be measurable in the nuisance. Okay. Now let us formally do the work. So that means we have to, when you say it is measurable, you have to say what is going to be just new sigma algebra and so on. So let us do it. So this is the theorem that we have proved. So let X be a measure space. Now we define M star. Define M star as follows. Okay. Defined as set of all E X such that there exists A, comma B belonging to M comma A, B, and measure of equal to 0. Consider this class. Okay. Now define mu star of E to be equal to mu of A, mu of A to 0. That means we are now bringing in more elements. So we get a new collection X So the question that you have is M star a sigma algebra? Next question is this: is M a subcollection of M star? Okay. Third question is 1, 2. Third question that you ask is mu star defined measure that is the third question that you are asking. And the fourth question that you ask is this. Oh, this we have already answered. Fourth question is this: is mu star an extension of mu, in the sense that mu star of mu e, whenever these are the four questions that we have. This we have already answered. Now you see, suppose, our whole intention is this. That is that if f is a integrable function on E, then every extension of that to the whole space X also should be integrable, and the integrals should coincide. Okay, so what do we get? Okay, then to take any f belonging to or take any of this. Okay, let E be equal to 0. Now, the first thing that you observe is that then a result that we prove immediately is that in fact that is obvious the way in which we have defined this. And mu star of E is well defined now. Okay. What do we mean defined? Suppose F is measurable, and we prove the following theorem. For any all its subsets are mu star. Okay. So what do? You take, let A be a subset of mu star of then and mu star of equal to 0 here. Okay. Then what do you get? You get mu star of A mu of empty set and mu of empty set implies mu of A B. So you start with any subset of E for which mu star of E equal to 0, then mu star of A equal to 0 for every subset A of. So this is what you call the completion of. So M star is completion of M. Okay. Now suppose you take a function on E and say E complement has measure 0. Then extend it to the whole space by setting it equal to 0 on the complement. Then the extension is certainly measurable in the old sense itself. Right? So any x by setting it to be 0 on E complement. Is measurable in the classical sense. With respect to E. That means what you are doing is F is measurable. Okay, let me put it this way. E then E complement has the property that mu of 0. Suppose F is measurable. In the new sense. That is F inverse of V intersection E belongs to Y. Now define and G equal to 0 on E complement. Is measured. If you were to define only as 0, then everything is fine. Okay. But this is not measurable. But there are extensions of f which are not. But suppose you give arbitrary values. They are not measurable in this context. On the other hand, no matter how one defines G on E complement, but G is equal to G is measurable in the context of that is the advantage that you have. Okay, and one also sees that integral of that is the integral of f and g are equal. This is because you see that between E and E complement, okay, in the sets in E complement are all subsets are now measurable in the new sets. Okay, so it is immaterial how you are going to set your G, or in other words, now you see that the F admits a larger class of extensions, okay, which are integrable and have the same integral as f on x. This is the important part, and this is the motivation for completing it. I hope I have made it sufficiently clear. Okay, so thank you very much.